What we're going to be doing today is the shift idea. We're going to go through all three of the key ideas of NMR, and you should have an idea what those are. We've reviewed them a couple times, what the shift or the delta value, and then the integration, and then what? The splitting. So the multiplicity patterns that they look like. And you see the table up here. We'll try to define that and relate things to structure. So even though we're doing spectroscopy, we're still talking about structure, which is a key idea in organic chemistry. But you see some of your favorite functional groups, alcohols, acids, aldehydes, they have different shift ranges, okay? And that's because within a molecule, all the little spin systems of all the nuclei add to the external magnetic field of the spectrometer, and they shift those signals around within that 0 to 10 ppm range. So that can help us out there. Now, let's talk about a little bit of history. So NMR was developed after World War II. And you know, there's a lot of nuclear research going on in World War II. Remember the nuclear bomb, the Manhattan Project, and that's a high energy event, right? We're talking about fission, breaking apart of those heavy radioisotopes of uranium and plutonium. We're not talking about that in NMR. We're talking about the nuclear spins, which is a very low energy process, but it is nuclear research. And Bloch and Purcell were into the whole nuclear idea. They were physicists. They won the Nobel Prize for NMR spectroscopy, but they were looking at a rather esoteric idea that nuclei do have spins, and that these spins are sensitive to radio frequency radiation, okay? We're not breaking the nuclei apart. We're not fusing nuclei together. Fusion and fission, those are very high energy things where the nucleus is changed, right? But here we're talking about nuclei that are spinning and then responding to this very weak energy of radio frequencies. Well, they finally built a spectrometer, and the story goes that Purcell at Harvard was one of the first ones to do it with a real molecule. And he said, okay, we've got an instrument here. We've got a magnetic field, and it's an iron core magnet. That's okay. We've built a RF generator, and we've built a detector. If they hooked their detector up to an audio speaker, they could actually tune it to the AM radio and listen to songs while they were listen to the radio while they were doing their experiments here. But he sent a grad student over to the chemistry department, the stockroom, to get a sample that had hydrogen in it. So we're talking about proton NMR, right? So they tuned their instrument to proton NMR, okay? They said, okay, protons are very abundant, H1, and the gyromagnetic ratio is very high. It's very sensitive to this, so it should work. They built the RF generator and the detector, and they went over to get a sample. And the grad student said to the stockroom guy, oh, I need something with hydrogen in it. What about hydrogen gas, H2? Do you have that? Well, yeah, it's a gas. It's a tank. You're going to have to contain that in your spectrometer. It's going to be a problem. Okay, what else do you have that has hydrogen in it? Well, and the guy said, well, how about ethanol? And the grad said, yeah, I'm familiar with ethanol. I'll do something with that. And okay, it's a liquid. Let's put that in your spectrometer and see what it does. So they started to sweep the frequencies here and tune their detector. They started at the high frequencies here on the left. This is the high energy thing. And they lowered the frequency down, and they weren't seeing any absorption, okay? Remember, spectroscopy is where you're irradiating the sample at a specific RF frequency, and then in your detector, you're seeing if it's absorbing anything, right? It's the same type of thing. Well, they kept sweeping down, and sure enough, look at that. They got a signal. It absorbed, and then when they passed that frequency, it decayed. And they said, yay, we've got it, it's working. Well, they kept lowering the frequency here, and look what happened. Oh, we got another signal. Wait a minute. Do we just have one nuclei in there? Yeah, we have hydrogen. Why are we getting two signals? And sure enough, they kept sweeping down further, lower, and wow, they even got a bigger blip to come out here. And at that point, they were perplexed, right? What were they worried about? They had one type of radioactive nuclei, right? It was responding to the radio waves. But what's up with these three signals? So they spent a lot of time checking their RF generator, checking their detector, making sure they had everything good there. They changed some things out. The electronics are, of course, very complicated with this. And they decided to run the experiment again. So here's our next experiment. Sure enough, yep, nice little peak showed up again. It was a little sharper. They had a little bit better electronics, whatever. And then this one came along here, and oh, look, we got another signal here. And this split into a quartet. Even more perplexing, right? This one stayed as a nice singlet, and they kept sweeping down. And yeah, sure enough, this one showed up again, but as a triplet. So double question marks here. So what's going on here? Well, they're seeing splitting for the first time. And they're seeing three different signals for the first time. And while this was annoying to physicists, the organic chemists looked at this and said, well, you've got 1, 2, 3 different sets here. Okay. And these three sets, they each experience different magnetic environments, right? So this one here next to an electronegative atom might be more exposed to the magnetic field, okay? This hydrogen here is different than these two hydrogens and these three hydrogens here. That's another experiment. They integrated this. This was worth 1 hydrogen. This quartet was worth 2 hydrogens, and this one was 3 hydrogens. And in the old days, they'd actually print out the chromatograms and cut these off and then weigh the paper and see what the weight of the different signals were. You can do that mathematically with the integration now. But so what's going on here? Well, the splitting idea, right? This one's on a alcohol, so it's hydrogen bonding here. It doesn't spend all its time on this oxygen, even though it does have neighbors. It'll always show up as a singlet, okay? So anything on oxygen or nitrogen will not show splitting. But what about these two here, okay? These two have 3 neighbors, okay? So these will be split as what? 3 plus 2, and it'll be a quartet, okay? Each one of these little neighbors has its own little mini magnet, okay? Each one of these is its own little magnet. We'll have to get into that and see how that works. But when we observe these here, it shows up as a quartet, okay? Because of the 3 neighbors. And what about here? If we observe these 3 here, how many neighbors do they have? They have 2. So that will be 2 plus 1, which will show up as a triplet, okay? And that's because their neighbors have little magnets associated with them too. Because there's 2, how they add to the magnetic field, they'll create this hyperfine or this splitting pattern, we call it. It's a quantum mechanical effect, but I'll show you qualitatively how it works. So Bloch and Purcell won the Nobel Prize for developing NMR, but it was really Jack Roberts at Caltech in the 60s who popularized it with organic chemists. And we said, oh, we're not bothered by this hyperfine splitting. We like it. Because this tells us something about the molecule, right? The kind of hydrogens, the number of hydrogens, and the neighbors, okay? So those are the key ideas. We'll get into this and talk about this. But first, let's talk about the number of sets in a sample. So here we have 3 sets, okay? 3 distinct types of hydrogens, we say. So let's go through this and talk about sets. And what do we mean by sets? We mean non-equivalent hydrogens, okay? And usually it's 1, 2, or 3, okay? Well, no, sometimes 6 or even 9 if it's a tert butyl. it's an isopropyl group, that's 6. So there are some magic numbers that kind of these patterns that we'll fall into. But let's look at a molecule like this. Dimethyl ether. How many sets there? 1. Okay, why do you say 1? This methyl and that methyl are the same because we have a mirror plane relationship here, or a rotational symmetry. So any type of symmetry that exchanges these two and makes them identical. So what do we say? 1 set. Okay. So they only expect 1 signal. And actually they have no neighbors. You can't split the set that's the same. If they're the same, that means they'll have the same shift. They'll have the same position where they resonate. So no coupling there. Okay. And plus, the neighbor here is oxygen. And that's not splitting it. So just 1 set. And you can't really tell by the integration because it'll be just that 1 signal. Okay. But the shift will be diagnostic. It'll be around 3.5 ppm. Okay. Singlet. We'll get into that later. Don't worry. How about this? Ethyl chloride. How many sets? 2, right? This will be distinct from that. So 2 sets. Okay. This one's closer to the chloride. We expect that to be further downfield, around 3 ppm. And this one will be closer to 1 ppm. Okay. And then the splitting pattern, it will have a triplet, it will have a quartet. Okay. So you're beginning to see already with these simpler ideas. How about this one? Ethyl methyl ether. How many sets there? Are the 2 methyls the same? Are they different? There's no symmetry that can exchange those 2 methyls. This methyl's on the end of an ethyl, so it's different than that. Plus, its proximity to the oxygen's different. So how many sets? 3. Okay. You're getting better at that? Everybody agree? Who's here? Okay, questions on any of that? Okay, how about this one? Ester? How many sets there? Hold up your hand. Somebody is saying 4. Does that make sense? Yeah, somebody says 3. Okay, let's figure this out. Is this methyl the same as that methyl? This methyl's next to a methylene next to a carbonyl. This methyl's next to a methylene next to an oxygen. So are those going to be the same or different? They're going to be different. Okay. So how many sets? In this methylene, proximity to that, you can see being distinct from that too. Okay. So the closer they are to these electron withdrawing groups, we'll have the shift value. This one will have a shift around 2.5. This one will be around 3.5. Okay. And that'll make the 2 methyls different because there's no symmetry operation, no mirror plane that exchanges these. So what do we say here? 4. Okay. Do you see that now? Somebody was saying 3, but I think we got that. Okay, how about this one? Cyclohexyl chloride. Yeah, a little bit harder maybe. But if you just look at the structure, this one's certainly distinct. Add in the hydrogen. They have methylene, methylene here. Those might be the same. You've got mirror plane relationship here, right? Methylene, methylene the same here. And then this methylene's different. Okay. So different, the same here, but a different set. And then these 2 the same, but a different set again. And then the methynes. So how many do you say? Somebody says 1. No, that's more than 1. What is it? 4. Okay, somebody says 4. And if you just look at this like this, you might be tempted to say 4. But let me tell you, if you've got a high enough resolution spectrometer, it's actually 7 sets. So what do we need to consider here? It's not just the flat drawing. What is the cyclohexane? So what is cyclohexane? It's not flat. What is it? It's a chair. Okay, let's look at the chair. And yeah, this is fluxional. You know, it's flipping back and forth between the equatorial and the axial. But when you look at like this way and then the symmetry, you know, how many sets do we have? Well, there's 1 set there. Okay. And remember the mirror plane goes right through it this way. This is coming out at you, right? And then we have this one, and those will be the same, those equatorial ones. And these two axial will be the same, but they're different than these two, right? This is trans to this chloride. These axial ones here are cis to this chloride, right? So we're already up to 3 sets. Do you see where we're going? Can we get to the 7? Let's see. So then you have this axial and this axial. Those are the same, but they're different set, right? And then you have the equatorial here, or here. And yeah, those are cis. These are trans to it. So that's, what are we up to? 1, 2, 3, 4, 5. Do you see where we get 7 now? Yeah, here it is. That one's trans to it. That one's cis to it. Now, like I said, this is a fluxional molecule, so you've also got this populated in the NMR. And that would be a different set, different group of signals. And it would broaden these lines. If you cool this down, if you do the NMR here at minus 78 degrees, then you can actually change the temperature inside the probe. There are ways to do that. And then you'll start to lock out this population. This will be the only thing observed. But how many sets will you see, actually? 7. You might have to have a high resolution spectrometer, a high field magnet. Like at 600 megahertz or 500 megahertz, you'd begin to see this. And I'll show you that, how at a lower field instrument, it may wash out. And some of these are flopping back and forth. And they'll be very close in their shifts anyway, and it might be less than the 7 sets. But the maximum number of sets is actually 7, okay, for that one. Okay, so it's a little bit tricky, right? Let's do a couple more of these. How about this one? Ethylene. How many sets there? Now, we're not trying to trick you now. How many sets? Be brave, come on. Just one, yeah. You have mirror plane here and mirror plane here. All 4 of those are identical. They'll resonate about 5.3 ppm. Okay, we'll see that. What the electronegativity of the carbon they're on has an effect for the shift too. How about this one? Fluoroethylene. How many non-equivalent sets now? Remember, a set can have 1 hydrogen in it, or 2 or 3 or 6 or 9. How many total non-equivalent sets here? How many signals will we see in the proton NMR? Be brave. 2? Anybody have another idea? I'm going to argue for 3. Okay, this one's distinct, right? Because it's on the same carbon as the fluoride. And then what about this one versus this one? Notice this one is cis to it, and this one is trans to it. So you actually have 3 signals, 3 sets. Okay. How about this one? Methylbenzene. It's also called toluene. Apply your symmetry idea here, your mirror plane relationship. The methyls, certainly 1 set here. And how about this hydrogen and this hydrogen? Well, you've got the mirror plane here. So these 2 that are adjacent to the methyl will be another set. So we're up to 2. And then these 2 here are 2 carbons away from the methyl. That's your 3rd. And then this one here is distinct still. So how many? 1, 2, 3, 4 sets. Okay. How about this one? Dimethyl cyclopentane. The 2 methyls are the same. You have a mirror right through the middle of the molecule. These 2, will those be the same? Yeah, because one is cis and one is trans, but you have a methyl both up and down anyway. So will that be a different set? Yeah, maybe. And then these 2 are the same idea there. You could draw a conformation of this. Cyclopentanes kind of have this envelope conformation, and you'd have these 2 methyls, which are kind of pseudo-equatorial, pseudo-axial, but it's very fluxional. okay? And these hydrogens here and here are always disposed the same way. In fact, you not only have a mirror through here, right? You have a mirror right through the plane of the molecule perpendicular to that. So that exchanges all of them, especially if it's functional, and you only see 1, 2, 3 sets there, okay? Hopefully you can see that. Is that okay? Yeah. Yeah, if you have this flopping up, maybe if we do this one, you see, this carbon right here is coming up and down, and that makes these two then the same. Okay. Yeah. All right. Let's see. Let's look at a little more detail of these sets. I'm going to use a couple terms here that might be a little tricky at first. Let's talk about topicity. Topology in math. We're talking about in three-dimensional space, how things are arrayed, right? We're already looking at that. These hydrogens and molecules are in 3D space, right? So we can talk about this idea of topicity. So homotopic, what does that mean? That means, well, we'll have hydrogens that are the same under all conditions, okay? So let's go back to this molecule, dimethyl ether. These hydrogens are all the same, okay? Rotational symmetry here, so we rotate around there, and then we've got the mirror plane relationship, and we've got rotational symmetry here. So it's just one set here, and we say all these hydrogens are what? Homotopic, okay? There's a way we can check this, and that's to substitute a deuterium on any 1 or 2 here. Let's put 1 deuterium in front versus 1 deuterium in the back. So it's kind of a thought experiment. We can specifically label deuterium and do a synthesis here. It can be difficult. But if we do this test, we say, we test for topicity using a deuterium substitution. What's deuterium again? It's the heavy isotope of hydrogen. Okay. Are these still the same molecule? Yeah. We rotate around here by what? 60 degrees. You see this deuterium would rotate to the front. It'd be exactly the same, congruent. Always the same. Okay. So homotopic hydrogens are always the same, so they'll be part of the same set. That's the way to determine it, actually. Okay. It's a little bit more detailed, a little bit more work to think about it that way with this deuterium substitution. What about this one? How many sets in propane? Let's go back here. Then we'll do topicity to figure these out. The 2 methyls here are the same, right? Do the mirror plane relationship, and the methylene is different. So how many total sets? 2. Very good. Getting more confident there. That's good. What about the topicity here? These 2 hydrogens. Okay, yeah, you see they're arrayed in the same position relative to everything else in the molecule. But you can do the deuterium thing. Are these still the same? Yeah, so you can see you just rotate it around 180 degrees and it'd be the same thing. So these are congruent. These are homotopic still, okay? Now, let's make things a little more complicated for you. Let's see, how about enantiotopic? So what do we mean here? Well, let's look at this guy again. Or I thought we had ethyl chloride. Well, let's do ethyl bromide this time. Okay, so these are different. Okay, what about these 2 hydrogens here? Let's do our deuterium study here. Okay, what do we have? Bromine, deuterium in the front, hydrogen, versus what, deuterium in the back, hydrogen in the front. Are those the same molecule now? What's the relationship between those two molecules? We don't have that rotational symmetry anymore, do we? We have this mirror plane relationship here. But notice when we do the deuterium substitution, especially on methylenes, this is where this shows up and can complicate the NMR. Methyls are almost always all the same. They're almost always homotopic because they can rotate around, right? And so they can exchange anything thought experiment-wise if we do a deuterium substitution. But now here, what's the relationship here? Are these the same? Are these congruent? What are they? What's the relationship here? Enantiomers, very good. Hence the name, enantiotopic. And here we're referring to these hydrogens right here, okay? And they're not the same. They relate as enantiomers to each other. And that means they're still always the same, except when they're in a chiral environment. And you can actually have a chiral solvent in NMR, or you can put in a chiral shift reagent, or a chiral catalyst, or any complexing agent that's chiral. Then these two hydrogens become different in the NMR. But for most applications we'll see, enantiotopic hydrogens will always be the same, okay? Most solvents we use are chloroform in NMR. That's not chiral, so we don't need to worry about it. But topicity, they're actually different than homotopic. Homotopic are always the same, either on chiral or achiral environment. But enantiotopic, because when you do the deuterium substitution, this becomes what? A stereocenter, right? We can have the R and the S one, whereas before when we did it with propane, did the deuterium exchange? It was still the same. There was no stereocenter there, right? The two ends were the same. But now the two ends are not the same, bromide and methyl. Okay, so this is enantiotopic. Okay, here's the important one. Here's the main reason why we're talking about this. This is a complicating factor in NMR. And I know Dr. Bronson likes this topic in 353. So master this idea now and you won't be annoyed by Dr. Bronson, okay? Well, we're helping you out here for 353. Here's our old friend 2-butanol, and that has a stereocenter already, right? So topicity-wise, some things are going to be complicated here. What about these two hydrogens here? Now that's certainly a different set than this methyl. It's a different set than this methyl, different set than this methine, and this hydrogen. So we might expect 1, 2, 3, 4, 5 sets, right? 5 sets? Oh, we got to check the topicity carefully. Let's do our deuterium experiment here. What do we have? This is a stereocenter. We'll keep it there. What is it? The R? Yeah. Let's do deuterium first in the front versus deuterium in the back. Now, what's the relationship? We already have a stereocenter here. When we do the topicity experiment here with the deuterium, is this a stereocenter now? Yes, it is. Look at that. Okay. Only when we do the deuterium. Okay. Here it's not a stereocenter, right? We only have the one stereocenter here. But when we examine the topicity, or the three-dimensional positions of those two hydrogens on that methylene, they're actually different now because of the proximity of the existing stereocenter. So notice I have this conformation right here, 180 degrees. If you look at that methyl to that methyl, if you look at the rotation there, that should be 180 degrees. Keep this 180 degrees to it. Okay. And you'll see this hydrogen here is what? 180 degrees to that oxygen. And then when we do the deuterium on the other thing, look, this hydrogen is what? What's that angle now? 60 degrees. Are those different? Yeah. And plus, this is the stereocenter here and here. Here we kept the stereocenter the same when we did our thought experiment. This became a stereocenter. So what's the relationship between these two molecules with the deuterium in different positions? What are they? Are they enantiomers? Are they the same? Or are they diastereomers? Very good. So we call these hydrogens what? Diastereotopic. And that's the third type of topicity. We have homotopic, where they're always the same. We have an enantiotopic hydrogens, where they're the same in an achiral environment, like normal typical NMR experiments. Don't have to worry about enantiotopic normally. But do we have to worry about diastereotopic? What do we conclude? These are diastereotopic, so they're always what? Different. And you can see why. In this conformation here, this one's anti, but in this conformation, this one's gauche, right? In fact, there's no way rotating around here that you'll ever make these two equivalent. They'll always be different. Why? Because of the proximity of this achiral stereocenter. Okay, see that? Build some models and see. These will always be different here. So do we have 5 sets? How many sets do we have then? If these are always different under all conditions, we have 1, 2, 3, 4, 5, 6. Ouch. That makes our life difficult because this will have a different shift. This will have a different shift. This will couple to that one. They'll both couple each other as doublets, and they'll couple over here as quartets. So this will make the NMR spectra quite messy, okay? So if you have any experience of the gesturin, have you seen diastereotopic hydrogens? Yeah, okay, in the lab they can pop up all of a sudden and you wonder, why is my spectra so complicated? Well, you have diastereotopic hydrogens because of that existing stereocenter. A lot of times if the stereocenter is far away in the molecule, they'll tend to be equivalent because the shifts will converge, okay? But especially if it's right next door, it's always different. You're always going to see that additional set, okay? So under all conditions there, if you've got an existing stereocenter, the methylenes typically will be diastereotopic hydrogens on that methylene. Does that make sense? Maybe? Okay, let's do a couple more examples here. I think doing examples of it, keeping the basics in mind is good there. How many sets now? Let's see this molecule. Now don't freak out too much because not all methylenes are diastereotopic. You have to have a stereocenter in the molecule, okay? So how about this molecule? What is this? 2,6-dimethyl heptane? Heptane, yeah. How many sets? This one's the same as this one, right? That's not a stereocenter. That's an isopropyl. And that's typical. The 2 methyls on an isopropyl fragment will be the same. How about over here? These 2. Yeah, you could rotate those and see there'd be a mirror plane right through there and another one the other way. So all of these would be the same, wouldn't they? Let's all be the same, okay? So we got 1 set, and then the methynes. Those are both the same too, right? No stereocenter. And then the methylene here, or another set. And it's different than that methylene right in the middle, right? It's further away from the methine. So that one's different than that one. But that one's the same as that one. So total it up. How many sets? 1, 2, 3, 4. Let me double check. Yep, 4 sets. Okay, not too bad. You'd actually have to have a high resolution, higher field instrument to tell those 2 apart. They'd both be around 1.2 Okay, these would be further up at 0.9. These would be around 1.8, 1.7. They do shift out a little bit depending on the type of alkanes they're on. But these two might be right on top of each other, so you may not see them completely resolved. So we're talking about the maximum amount of sets here most of the time. Okay, how about if we put a methyl right here? Now how many sets? Now I am getting tricky. So we need to be careful here. It's not 4, and it's not just 5, not just adding another one there. And these are all different now. And what do you need to look at first here? This is what now? There's something special about that methine. It has 4 different groups on it, right? So what is it? It's a stereocenter, right? Which means what? All the groups here relative to each other will actually be diastereotopic. You can draw in the stereochemistry if you'd like. Draw in one enantiomeric form. It's racemic though, it doesn't matter. Racemic chiral molecules will still have things be diastereotopic. It doesn't matter whether you have the one enantiomeric form or the other. So this will make these two different. Okay, it'll make these two different also. So we're already up to what? 1, 2, 3, 4, 5, 6 sets. And these are different now. That's 7, 8. What about these two here? You can do your substitution on those, and you'll actually see if you do these differently with CD3 here versus CD3 over there. Those can actually be diastereotopic also. That's a little bit trickier. So these are different. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 sets. And if you analyze it and do the deuterium exchange thing, you'll see this becomes a stereocenter when you compare that one deuterated up there. Those are 4 different groups. And by the definition, because of this existing stereocenter, these would also be diastereotopic. Okay. So, yeah, the individual hydrogens in a methyl are not. Those are still all the same, because if you did deuterium here, you could just rotate those around and exchange those, you see. Yeah.
So you replace the hydrogen then with a methyl group?
Yeah.
Wouldn't be, right? Because you just rotate around that
Well, we'd have to compare it to this one here. Okay.
So if they're, sorry, the hydrogen on the second carbon there,
The methine?
if that was a methyl,
Oh. So the question is, if we had this hydrogen become a methyl, now this is a tert butyl. Yeah, now a rotation around here. These are all homotopic. Yeah, okay. Yeah, so don't worry too much. Mainly for this class, if you see a stereocenter, the methylene hydrogens will be diastereotopic. Okay, that's the main thing to look at there. Okay, one more here. Oh, maybe a couple. How about this one? Speaking of tert butyl, that's a good lead in here. How about tert butyl benzene? And how about this guy? Back to tert butyl methyl ether. Okay. So what about this? Is there a stereocenter in either of these molecules? No. So these things will be the same. All 9 of these are homotopic. You can do the thing exchange. Same thing here, exchanging here and here. These two are the same. Okay. Because you can just rotate around the benzene, right? And then these two are different, and this is different because of the proximity to the tert butyl. So how many sets in tert butyl benzene? 1, 2, 3, 4. 4 sets. And no topicity issues. No diastereotopic. That's what you need to look for. How about this one? Same thing here. How many sets? In fact, we saw that already. I showed you the spectra last time of this ether. How many sets were in there? 2. Okay. All right, questions on this? So nailing down the set should be okay, and that's a topic here in quiz 8. So let's go back and look at some of the factors that affect shifting. And the first thing to look at is electronegativity, how close things are to electronegative atoms. So let's look at these molecules here. So here's a series of molecules going across the second row of the periodic table, looking at electronegativity of the group that it's on there. And fluorine is 4.0, oxygen's 3.5, nitrogen's 3.0, carbon is 2.5. So the most electronegative, I guess it's the reverse order of how we look at the periodic table. Normally we have fluorine on the right. Here I've got it on the left. But let's look at the shift now of the methyl group that it's attached to. Okay? And the shift here is 4.3 delta ppm. Okay? That's quite a ways downfield. Okay? And what about on the oxygen here? Its shift is 3.2. That's typical for any group, alpha to an oxygen, we say. And then alpha to a nitrogen, what do we have here? For the shift, it's 2.2. And ethane, they're both the same. We're comparing bonded to carbon. No electronegative heteroatom here. This will resonate at 0.9 ppm or delta. Okay, so what's going on here? Let's look at fluorine and these hydrogens. So we're looking at these little magnets spinning in the presence of the external magnetic field, right? But if we have a strong inductively withdrawing atom there, what's that going to do to the electron density around these nuclei? This is perturbing the electron cloud of the molecule, right? So it's pulling these electrons in the entire molecule toward itself. That leaves the little nuclei more exposed to the magnetic field. And we say it's what? De-shielded. De-shielding these hydrogens in that they're more exposed because the electron cloud is being withdrawn. Okay? If the electron cloud remains electron rich, we say the signal is more shielded. Okay? And it shifts to a lower frequency. This requires a higher frequency to flip these spins, to make them resonate, because the electron cloud that's normally shielding those nuclei is being polarized toward the electronegative. So that's the thing. It's an inductive effect, which has to do with electronegativity, which affects the frequency that these things resonate at. And that's part of this, right? That shift, that ppm value we saw before. This is a higher frequency. This is a lower frequency. Shielded versus de-shielded. All right, let's look at another one where we've got multiple electron withdrawing groups. How about chloroform versus methylene chloride versus chloromethane versus methane? Okay, what's the shift of those hydrogens in the proton NMR? Here we've got 3 here. We've already seen this one actually, 7.3 delta. How about methylene chloride with 2 hydrogens? Okay, so it's an additive effect. If you have 3 electronegative groups, that'll make this shift even higher. Okay, the inductive effect is multiplied and 0.9. Okay, so de-shielded versus shielded there. All right, let's look at hybridization. And this is the other main idea. Proximity to electronegative groups will tend to make things more de-shielded, higher frequency. Hybridization, let's see. So we've got methane, sp3 hybridized. What's the delta here? 0.9. And then we've got these on alkenes. What, sp2 hybridized, right? sp2, more S character, right? It's pulling these electrons a little bit more here. Whereas these have less S character, They're donating electrons a little bit more, and it's what? Highly shielded. But what about here? D-shielded, 5.3. And what about aromatic? 7.3. What went on there? That's still sp2, but there's some other effect we'll have to talk about there. And what about this? That's sp. Okay. Let's see, if sp2 are way up here around 5 and 7, where should sp hybridized be? Higher or lower? It's 50% S now. So what should it be? Higher. You might guess 10. Okay, it turns out it's 2.3. There's a significant shielding effect that has to do with this. In fact, these topics here have to do with diamagnetic anisotropy. Another tropy name, diamagnetic anisotropy, and that means in three-dimensional space, the extramagnetic field created by a ring current of electrons in a molecule can change how the adjacent spins see that extramagnetic field. So these are going to create new magnetic fields. Let's start to look at those. We got a couple minutes. Let's go back up here, Jeshurun, and see. So here's the shifts we've been talking about. Here's the alkene thing. If it's sp2 hybridized, goes a little bit higher than, of course, around 1 here. And aromatic, yeah, around 7. But look at alkyne here. sp hybrid drops down to 2.5. Something strange here. Proximity to heteroatoms, yeah, that's good. So for one carbon removed, like at the alpha position to a carbonyl, yeah, we're around 2, 2.5. If we're right on a carbon with an oxygen or a nitrogen or a halogen, then we can be all the way down to 4 or so. And that's additive if we have a bunch of electronegative groups even further. Aldehydes around 9. Alcohols and carboxylic acids, these are in hydrogen bond exchange, and that'll affect their shift. It can be variable depending on the concentration, because that determines how much hydrogen bonding exchange there is. And this is a weak acid, so that's exchanging that fast too, but these will have different shifts there. Let's see, yeah, here's diamagnetic anisotropy, we're looking at that. And this is because we have this circulating ring current. We'll have to look at the models tomorrow and go through this carefully, but if you have a ring of electrons, right, and in a pi bond or an aromatic group here, you have all these p orbitals full of these pi bonds, electrons, right? Well, they can create their own little electrical field. And perpendicular to that electrical field, which is circular, you have this toroidal magnetic field that's created by the molecule. So these hydrogens within the molecule feel the combination of the external magnetic field. This is your big magnetic field of your spectrometer. And here's our little magnetic field created by this ring current of electrons, okay? I'll draw this on the board, and hopefully my artwork will convince you of this, but the electrical field's right here, the magnetic field's perpendicular, and you see that the hydrogens experience an additive magnetic field because of the toroidal shape here, and the pi electrons of the benzene line up to actually oppose the external magnetic field. Here it's opposing the magnetic field. But on the sides of the molecule, it experiences an extramagnetic field, which leads to a higher shift, goes up to 7 ppm. So we'll leave it there. We'll do alkenes and alkynes. We'll see why the alkynes are a little bit different. And yeah, we'll start solving problems. We'll go back to structures and hopefully figure things out. So we'll see.